Okay, welcome. So, what I'm going to be covering today, just another lesson on refraction, but this one will have to do with lenses. So, this will connect kind of what we were talking about yesterday with, or in the previous lecture with indices of refraction, but also to some of the more common technologies that we see today. So, I'll just go ahead and share the notes. All right, there we go. Okay, so basically what we're going to be looking at, like the first essential phenomena is going to be refraction through a circular, spherical, or in general, just a curved object. Like all curved objects do this. Um, uh, uh, Curved, let's say medium. Um, all curved objects do this to a certain extent. So for instance, you can actually get some focusing with you can actually get some focusing effect with the with just like a clear 2 liter soda bottle. You can actually get this to work. It's kind of interesting. But in any event, I want to just kind of show you what I mean by this. So basically, instead of having, something actually, let's do this. Yeah, that's fine. Okay, cool. Um, so instead of having a rectangle, like a block of transparent material, what you have now is sort of either a sphere or a cylinder of transparent material of some kind. So the question then, okay, what does this actually do? Well, it depends where the rays strike it, depends how they strike it. So what I'm going to um start by drawing just kind of a dotted line roughly through the center. Um, and let's say we have a ray of light that's going like that. Well, the idea here is that this ray is actually perpendicular to the surface because it's going to go through the radius, which is actually perpendicular to the edge of the circle. Okay, so this ray is just going to continue straight on through like that. Now, if we have another parallel ray, so these two are parallel up here, but it doesn't strike the surface at it's kind of going above the diameter like that. Well, what we would need to do is we would need to draw a perpendicular. Now, the easiest way to do that is just extend a line from the radius that is perpendicular to the surface right there. And then I can do a dotted line just to do the apparent path of the ray. And we know that the actual ray is going to be bent towards the perpendicular. So it will look something like this. Okay, so it's kind of getting pushed back towards that center ray. Now we do one below it, and you can imagine that basically the exact same thing is going to happen, except this one gets pushed up. Okay, so again, we have the dotted line and it's going to go something in between those two. So this one is going to get pushed up. And what you can see is these are all kind of they're converging on a single point, and that point is it looks to be right about on the other side of the circle in this case. It's not relevant where that happens right now, but it is relevant where that happens. It's not relevant that it seems to be happening on the opposite side of the sphere. It depending on on how big this thing was relative to the light. Different things would do different things. In any event, what we have here, the idea here is that parallel rays of light will converge, and this is an important term, to a single point called the focus. Okay? So when you hear about the focus of a lens, it's basically referring to that point where the light is going to converge. Now, typically we don't use some lenses, some very good lenses are actually spheres. If you can get a perfect sphere of glass, this was an early way to make very good lenses. Antoine van Leeuwenhoek, the inventor of the microscope, this was how he made his lenses. Nobody really knew how he did it. Basically, what he did, it turns out, is he just melted little pieces of glass. So they would drip off and they would harden on the way to the ground. And it turns out that like a liquid in free fall will naturally form a pretty tight sphere. And so he was able to get these lenses, these spherical lenses that he used in his microscope in this fashion. And this was how he was able to do some pretty impressive work for the time period. He's definitely worth checking out. Antoine van Leeuwenhoek, or just look up inventor of the microscope if you're curious. Now lenses today, most of them are not spherical. Like you can use a sphere as a lens, but typically what we do is we use what's called a thin lens. And basically, what a thin lens is this is a the curved portion of a sphere that does the bending of the light. Okay. So in the sphere, there's a lot of glass there. And that the fact that like that sphere could just as easily be hollow. It's much more difficult to make a hollow glass sphere than it is to make a solid glass sphere. But you don't need finish this sentence. This is the bending of the light. But you don't need all the glass in the middle. As a matter of fact, that can sometimes be difficult, or it can sometimes present problems, particularly when we think about what we talked about yesterday with prisms, that if your colors are refracted slightly differently, basically, and you don't have monochromatic light, you don't have light of a single color. Basically, what can happen is you can get this effect wherein the color will start to separate. That's a type of lens aberration that is somewhat common, and a lot of times it needs to be corrected for. So this is one of the things that ends up doing that. Is this thin lens. And basically what a thin lens looks like looks much more like what you'd find in a magnifying glass. It's basically just something like this, where you have the two curved surfaces, but not all the intervening glass in the middle. And the idea is that this does exactly the same thing. So we still have this center line. We call this the axis. Whenever we do ray tracing, we almost always need to draw the axis because that is going to be relevant. And then we will talk about having a focus on each side, or a focal point on each side. And this we call F. And that is F, and F is the focal length. So it's the distance from basically the center of the lens to where the focus of the lens is originated. And basically what this means is that if you have the parallel rays of light like so, they will all be bent towards the focus. And we could even draw some more in here. All of these will ultimately be bent towards the focus. So if you've ever used a magnifying glass to set a dry leaf on fire or something like that, don't suggest that, but it is kind of cool to at least test that out, as long as you're safe. This is basically what's going on. You're getting a whole bunch of parallel rays from the sunlight collected by the lens, and then you're concentrating them all into a single point, which does get quite intense and it gets quite hot. So this is one way that if in a pinch you could start a fire this way. You do need tinder. It's not magic, but it is something that could be done. Now, a couple of things I want to talk about that come up with these thin lenses. By the way, this type of lens right here, this is a converging lens. And the idea, converging lens, also called, you'll see these sometimes called convex lenses. And that's because the surfaces are convex. Now you can have like one surface be convex and one surface be flat. It's still a converging lens, which is why the term converging lens is a little bit better. But nevertheless, this is that's what this is called. And the whole idea is it's converging because the parallel rays converge to the focus. Now, this will be contrasted with a diverging lens to the focal point, where the opposite will happen, but we'll get to that in a bit. Now, the other thing I want to talk about is radius of curvature. And basically, the way you can think about the radius of curvature is that if the lens was a complete circle. So either a sphere or it could be a cylinder. But if it was a complete circle and you were doing this, basically the radius of curvature, R sub C, is equal to the radius of that circle. All right. So let me just show you kind of what I'm talking about here. Now, ultimately, what you can have is you can have let me just draw a small thin lens. The idea, so that would be a thin lens. The idea is if this thing was if you made a complete circle out of this, basically this thing right here would be the radius of curvature. Okay. Now the connection that is relevant, and this is for thin lenses. Okay. And the reason it works for thin lenses is we basically what we want is we want the curvature to bend the light, but we don't want but we want that bending to be fairly predictable. So ultimately the focal point would be determined by the index of refraction, but for thin lenses we kind of ignore it. We say, okay, it's sufficiently different that it generates this effect, but we're not going to look at the precise variations. Instead, what we make this approximation where we say, okay, 2 times the focal length is equal to the radius of curvature. Another way of doing this is saying your focal length is your radius of curvature over 2. All right. So your focal length would be, kind of right there. That would be your focal point. The length would be the distance from the center of that to to the the focal point. Okay. So that's something worth remembering, but that's basically it. Now, the coolest thing about lenses is that lenses can project images. And when you think about a lens as either magnifying something, um, so this can be done in the form of some sort of magnification. It can be done in the form of some sort of demagnification. Sometimes this is useful. Or in the case, it can be used to directly, and when I say project an image, basically what I mean by that is shine an image onto a surface. Okay, so the main idea here is something like a camera, a movie projector. All of these things ultimately use lenses to project that image. Okay, so the idea here, the way we figure out and this image projection is something we can analyze, and we do this with ray tracing. Okay, ray tracing is basically the process of looking at the images generated by objects or the light from objects in the presence of lenses. Okay, so finding images projected by lenses. And there are 3 rules when it comes to ray tracing. And the 3 rules are not that difficult to remember, but they can be difficult to apply. So 3 rules. The first rule, rule 1, is that a ray parallel to the axis will be bent such that it goes towards a focus. Now, with converging lenses, it's easy. With diverging lenses, it's a little bit more tricky. But and all of the rules are a little bit more tricky with converging lenses. But I want to leave some space and just show you kind of what I mean here. Okay, so I'll make this a little bigger. Diagram can be a little bit bigger. Okay, so we have a we have a lens and a dotted line. Now, basically what I'll do is I'll just have a little point of light, and this light is going to be emitting rays. Okay, so if this ray is, and I'll draw the, we'll say the focal length is right there, and really it's better if you do this actually geometrically. Like the geometry of this is actually quite interesting if you do it correctly with rulers and other things like that. But basically what you have here is you would have a parallel ray going like so. And the way I usually do it is right in the middle. Like you'll get some bending at both surfaces, but right in the middle, I usually just say, okay, what's going to happen here? This thing is going to go down towards the focus and just continue on like so. Okay. Now that's the rule we've kind of already seen. But the second rule is that a ray, I'm actually going to back this point up a little bit just so that doesn't really change anything, but with the next one it'll be easier. A ray through the focus will be refracted to parallel with the axis. All right. Now, what do I mean by this? Okay, so I'll number this one 1, and then I'll do the next one in purple, and I'll color code that number 2. Basically what I mean is we start from the same point, we go down through the focus, and then once it interacts with the lens, then this thing becomes parallel to the axis. So that is effect number 2. Okay. Now the third rule, and a lot of times those two are sufficient, but the third one is also helpful to know. Because basically the idea is that, okay, if we do this, we're going to have where these two rays meet, this will be where the image will be. So if that dot I did there was an object, where the two rays meet was an image. But the third rule is that any ray through the center will continue in a straight line, as I should say, of the lens. Will continue in a straight line. So the idea is that some of the rays are completely unaffected by the lens. They slow them down a little bit. I'll do this one in blue. They slow them down a little bit, but if I have a ray going right through that point right there, then I don't change it at all. And you'll notice that even freehand, all those 3 rays should meet at the same point. Okay. And so that is basically what we're seeing there. Okay. So those are the 3 main rules. Now, the way I want to do this, I want to do an example with an object and just kind of show you what this implies. So I'll start this off. Well, when you do ray tracing, you generally let your object just be like an arrow. So this thing right here will be my object. And then I'll have my lens like so. And then what we have here, the distance from the object to the lens, we call this d sub o. So d sub o is distance from object to lens. And it's important to note that this is something you could deliberately control. Whatever you're looking at with the lens, you can change the positioning of your lens to change that. Now, also relevant that d sub o is greater than 0 in this case. Even though it's to the left of the lens, we still define it as greater than 0. So sometimes the sign conventions are a little bit confusing, but that's what's going on with this. Now, the idea here is that this thing is going to make an image. Now, I'm going to make my focus be right about there. My focal point will be right about there. So we will also label that F. That's just called the focal length. And then I want to have one on both sides because we'll actually need both of them. Okay, so you need to have your focus on both sides to do this ray tracing. Now, once we have that, we can do the ray tracing. And I'm just going to do a ray trace with blue lines just to be clear. This one is fairly easy where you just do parallel. And then once you hit the lens, you angle it down through the focus like so. Okay. Now, I also think the central one is pretty easy because you would just do not quite like that. Like I say, much easier if you have a um if you have a if you have a ruler. But in any event, goes through there and meets at those points. Now, the last one we have goes through the focus, and then it should go parallel out. And you see, I'm a little bit off, but basically they all meet at the same point. Now, the point I originated, this was the top of the arrow. Um, the other point we have, so basically what this means, this is going to be the top of the arrow right here. Now you're like, wait a minute, it's below. That is true. And basically, our image, I'll draw the image in purple, our image goes downward. So this right here is our image. Now you can tell the image is actually looks a little bit smaller, but not only is it smaller, it's flipped. So image is flipped. Now, a big part of the lab is investigating is the image always flipped? Is the image always smaller? I'll just put and smaller here. Those things are things you'll be looking at. But basically that's what's going on with this. Okay. So that's why you have that going on. Now I do want to show you one other example of this, of what happens when this is going to be something more like what would happen if you were using a lens as a magnifying glass, and I'll make the lens pretty big. And this time I'll make the focus way out here and, roughly out there as well. And I will take my object just like so. So here's my object. And this time, notice I'm putting my object in between the lens and the focal length. Now, it's a little bit counterintuitive how this works. I'll do it with blue again. First one's still super easy. We do parallel, and then that bends towards the focus, okay? Because it's still a converging lens. All right. Now the next one is also somewhat straightforward. Nothing really changes there. We just go through the center. And you might be looking at this like, uh-oh, this seems a little bit odd because I'm going to do this one slightly differently. Okay. This seems a little odd because these rays are only getting further apart. Like at the focus, they're further apart than they were at the lens. Well, it turns out the same is true for the other one, but we need to be careful. So if we want a lens, a ray going through the focus, what we'd have to imagine is we'd have to backtrace a ray. So I'm going to do that in a dotted line from the focus to the top. And then that goes to the lens. So that's the ray we want. So that would actually be our second ray there. So this would be ray 1, ray 3, and this is ray 2 right here. And now this thing then goes parallel. Okay, and notice these three rays are never going to get closer. So do they make an image? Well, not one that you can actually project onto a screen, okay? But what is interesting about this is if we backtrace these rays to sort of imagine where they would meet if this lens were, if we had these three rays, but this lens were not here, where would these rays actually meet? So I'm going to backtrace these in green. Okay, so this first one, it's just backtraced horizontal to the to the um to the plane there. And then this next one is backtraced, and you can see now they do actually meet at a point. And with a little bit of inventiveness, we can see that, and it's not quite right. This has to do with me doing it freehand, but they basically meet behind the object. And this is what we call a virtual image. Okay. And so this is a virtual image. And the idea is that if the image is formed, um, basically behind the object using those back traced rays, then it's a virtual image. Now, a virtual image doesn't project onto anything. What you need in order for a virtual image to be useful is you need some other lens to ultimately convert that into a real image. Now, that is what the lens in your eye does, okay? The lens in your eye converts this virtual image into a real image that's then projected onto your retina, which you then perceive. So this is why when you hold a lens up to a small object, the object looks bigger because you're basically changing the light from that object so it looks like it's being projected from a virtual image, okay? A bigger virtual image. And that's ultimately how that works, okay? So that's the idea. Now, in this case, I wanted to talk about one other thing. This right here would be DI. That is DI is the image distance. Now, in this case, DI is greater than 0, okay? So we kind of use just kind of the natural progression of light to define your object and your image distance as both positive, even though they're on different sides of the lens. That's just basically how we do it, okay? Now, for the case of this one, what we have here is we have this guy right here is our object distance. And then this right here is our image distance. Now, object distance for this one is still greater than 0, but image distance is now considered less than 0. Okay, so we give that image distance as a negative number. All right, so that's basically what's going on there. Okay, so that's worth keeping in mind. And it comes up in some of the equations, which we'll talk about soon. Now, I do want to also talk about diverging lenses or concave lenses. So diverging lenses, the line here, or also called concave. Now, again, diverging tends to be a more descriptive term because it's what the light does, whereas concave is more a description of the shape of the lens. So we'll go. I'll just try and I'll do an axis first so we can do this. And then I am terrible at drawing these correctly. So basically what it is it's kind of the way you can think about it, it's kind of like the it's kind of like the opposite of a converging lens, where a converging lens was thick in the middle, thin on the edges. This is thick on the edges, thin on the middle. And basically what happens here is that the rays, whoops, that's too big. To red. The ray on the center still goes straight through. But what's interesting is, and I'll mark give a focus here. It should be a little further out. If we have another parallel ray, what's going to happen here is when it hits this lens, it's not going to bend towards the focus, it's actually going to bend away from it. But how is it going, like how much is it going to bend away from it? Well, the way we determine that is we'll basically do a dotted line from the focus to where the ray gets bent, from the focus on the other side. And then this ray traces up and away like so. Okay, so this time the rays, the light rays are being spread out. And then same thing if we do this down here. So again, I would do a dotted line kind of like so, and then I would guide this ray along like that. So that is how a diverging lens would differ from a converging lens. Okay, so that's worth keeping in mind. Right. Okay, what next? Oh, I wanted to do an image projection with one of these things. Okay, so it turns out I just wanna be clear that because these things diverge, no real images are generated. only virtual images. So you cannot use a convert or a diverging lens to project an image. You can use it in a lens setup that can project an image, but you ultimately need a converging lens to project an image. But you can create virtual images, and it turns out that many eyeglasses, because way more people have myopia or nearsightedness than farsightedness, and this is the kind of lens you use to do that, or to correct for that. That the virtual images they project can be quite useful. All right, so the idea here then is that we'll do another, I'm trying to give myself enough space. We'll do a, again, you see, I can almost never make these things symmetrical. Um, we'll have our focus there, and then we'll put the object right here. Okay, so actually, I'll give myself a little bit more space. So my object will look like so. All right. Now, the question is, okay, what is going to happen here? So I'll trace these rays out with blue. Now, the one that I think is easiest is just the one that goes through the center. This one changes not at all. It just goes straight through the center. So that one is essentially identical to what we did with the other type of lens. So that seems fine. When we have the parallel ray, we already know from above that this one's gonna, we already know what this is gonna do. This is gonna backtrace through the focus, and then that dotted line tells us the direction of that ray. So we can already see that these two rays are definitely not gonna meet. Now, for the really, this is the second rule, but it's kind of the one that's hardest. For um for convex lenses or converging lenses, we traced a ray through this focus. For diverging lenses, we actually backtrace a ray through the other focus. So what I'm going to do is I'm going to do a dotted line that goes basically from the tip to that focus. Now, the initial ray goes along the start of that path, but when it encounters the lens, that's when it goes and ends up being horizontal. Okay, so I think I drew that slightly angled, but in any event, you can kind of see what it would look like. It would look kind of like that. All right. Now, what to do from here? Well, what we would ultimately want to do from here is we want to backtrace all these rays. Now one of this ray does not need to be backtraced, it's already there. We already have our backtrace of this ray, so we can kind of see we're going to get our image point right there. If we backtrace our refracted ray, again, like as if this parallel ray was like a straight line, it basically meets us at this point. So right here, we would have our image. Now note, it is a virtual image, but it is smaller. Okay, so virtual image, and it's smaller instead of larger. Now, are there ways to generate larger virtual images with convex or concave lenses or diverging lenses? That is an interesting question. That would be worth investigating. But I'm basically going to try and show you a method, not necessarily try and give you all the answers. So this is a virtual image, and it is smaller than object. Okay. All right. Now, it turns out that with a lot of these diagrams, you can do some geometry to come up with some relationships about how how the how the distances involved relate to one another. I'm just going to go ahead and give you those equations. So the first is the Lensmaker equation. And it looks like this: 1 over d object plus 1 over d image equals 1 over the focus. So I believe I have all the signs right there. I just want to make sure of that. Equation. Um, Or no, sorry, this is not the lens maker equation. This is the focus equation. I'm not going to go into the lens maker equation. That relates to to the uh, to the index of refraction to the and the radius of curvature. Not gonna bother with that. Um, so I just like I say, I'm pretty sure. Yeah, that's the signs are correct there. Okay. Now it is important that you get these right. So just as a reminder, DO is always greater than zero. DI is greater than zero for real images, or for images, the way you can think about images to right of lens. Now I'm generally, just as a matter of convention, I'm putting the object on the left of lens. But that's the idea. Now DI is less than zero for virtual images. Now, we didn't talk about this, but it's important to know that mathematically you can distinguish between a diverging lens and a converging lens with the focus. So f is greater than zero. This is for converging lenses. Okay, so you give a positive focus if your lens is a converging lens, kind of like a magnifying glass. Your f is less than zero for diverging lenses. Okay, so this is some of the sign conventions that are helpful to keep in mind. Now, this one basically, f is determined by the lens. Your DO is almost always set by user, not always, but you can basically, this is something that tends to be independent. Again, like I say, not always. Like if you're constructing a telescope, a lot of times you'll just let DO be functionally infinite, in which case it turns out that you basically want your image is basically going to be projected at the focal length, but that's it's a little bit beyond the scope of what I want to talk about. And then this is generally what you determine. So what is determined? Now, again, this is not always true, but this focus equation, focal length equation, that's what I'll call it, focal length equation. Like, I'm not gonna go into the lens maker equation. I don't know that there's necessarily much point. Next one is the magnification equation. And basically, when we think about magnification, what this is how much the image is, how much larger or smaller than the original the image is. So the fundamental way this works is we just do the height of our image over the height of our object. Now it's worth noting that magnification is greater than if magnification is greater than zero, then the image is upright. If the magnification is less than zero, the image is flipped. Okay. So when we think about, looking back at the very first one we did, this would have a negative magnification. And again, what we mean by that is we don't mean the object got smaller. We mean that the image was flipped. Okay. So M is less than zero for this one because that image is flipped. And as a reminder, like that height would be measured, from the axis to the top. That would be the height of the object. But it's going down with the inverted image. So hopefully that can make sense of why those things do what they do. So why those signs work out. Now it's also worth noting that if the absolute value of magnification is less than one, then basically what you have is you have a smaller image than object. So this is what happens when you don't get magnification, when you get shrinking, basically. And again, like I said, sometimes this happens. Okay. Sometimes this is useful. Now it turns out that you can do some fancy little trig and you can just end up with, okay, actually this is equal to the negative distance of the image over distance of the object. You can basically prove that basically by setting up some triangles here. That would not be that wouldn't be a big deal to do that. But in any case, what I want to do is just want just to verify with the signs. As a reminder, your DI and DO are both positive for real images. And that's why this negative is needed to basically make it converge or to jive with the signs over here. So this means that again, if your image is inverted, well, that means it's going to be real, which means you're going to have this kind of magnification here. I'm sorry. Okay. Now, this second part doesn't work. It's a little bit more difficult to determine what this means when you have multiple lenses. But this, the height of the image over the height of the object, that is a clean way to always calculate the magnification. Okay. So I think, oh, I do have one more thing I want to talk about. Here's my mouse. Okay. And that is the power of the lens formula. If you have glasses and you've ever looked at your prescription, that first number is the power. The other ones involve correcting for astigmatism, which I'm not going to go into. But the power is basically a relation of the focal length. Now, D is the power, is 1 over the focus. Now, the idea here is that so if D equals -2, that's what it is for my left eye. My power is for my left eye. That's why I use that. Basically, what you're saying is that your focus is equal to -1/2, and it is an SI, so it's -1/2 meters. Now, the reason they don't just use the focus, the reason they take the power is as your focus gets smaller. Remember, that's a tighter and tighter lens. The lens is distorting the light more and more because you're getting a smaller and smaller focal length, which means that the lens is affecting the light a lot more. It's more and more different from just straight glass. Okay, which basically straight glass doesn't have a focal length. The light doesn't converge at all. So basically, they wanted the number power to sort of reflect the strength of the lens. Whereas if your focal length gets smaller and smaller, that's indicating that the lens is stronger and stronger. So that's why they use this power formula. So D is just equal to 1 over F. That's one thing to remember. Okay, so that is all I wanted to talk about today with these questions or with these topics. So I'm gonna go ahead and end it there. I will probably just do one more recording. This one will be good to check out for the lab, but there'll probably be just one more recording, and then I will field any review questions people would like to have and possibly make some recording there if they are in demand. So thank you for joining me today. I will see you next time.